Okay, this is the review for chapter 4, and we borrowed a section from chapter 25. I think it was 25.3, but it was mostly chapter 4. Let's talk about what was in there. Chapter 4 is going to have, what, two, five, 8 questions out of 40 on the final exam. So let's remind ourselves what we covered in chapter 4. Chapter 4 was on atomic theory, which basically is what's an atom and what's in an atom. So we talked about the subatomic particles. You should be familiar at this point with the subatomic particles: protons, neutrons, and electrons. You should know their mass and their charge, right? Remember, protons and neutrons weigh 1 atomic mass unit. Electrons essentially weigh zero. Protons are positively charged, neutrons are neutral, and electrons are negatively charged. Um, the protons and neutrons are found in the nucleus, and the nucleus is incredibly small. If an atom is small, the nucleus is like a marble in the middle of a football field, football stadium. So if the whole atom was the size of a football stadium, the nucleus would only be the size of a marble at the 50-yard line. That's where all the protons and neutrons in the atom are found. The size of the atom is defined by how far out the electrons will go. But all the mass in the atom is found inside that little nucleus, because all the protons and neutrons are the ones that have the mass. Atomic number is the number of protons. An element is defined by its number of protons. Mass number is protons plus neutrons. You should know that the atomic mass of an element is the weighted average of its isotopes, which brings us to isotopes. Isotopes are versions of an element. They are atoms with the same atomic number, but different mass number, because they basically they differ in the number of neutrons. Right, so they'll have the same number of protons, but a different number of neutrons. So each isotope we talk about in terms of its mass number. That's how we identify an isotope. So boron 11 versus boron 10. Boron's atomic number 5. So boron 11 would have 5 protons and 6 neutrons, because 5 plus 6 is 11. On the other hand, boron 10 would have 5 protons and 5 neutrons, because 5 plus 5 is 10. Right? So those are the isotopes. And the atomic mass for an element is the weighted average of the atoms of that element found in nature. Okay, so you should be able to know how to calculate the atomic mass. You can, when we had an equation where we're just basically calculating a weighted average, and we can estimate the atomic mass using the mass numbers. If you know what isotopes you've got and what percentage uh, each isotope is in nature, you can use the mass numbers to estimate the atomic mass. It'll give you a number really close to the number on the periodic table for atomic mass. But if you want the actual atomic mass, you have to calculate using atomic masses. And those atomic masses are the atomic masses from the for each isotope from spectrometers. So they weigh them to the nearest, millionth of a atomic mass unit, and you use those numbers in order to calculate the atomic mass. Okay, that's what we covered in chapter 4. Uh, Probably our big calculation there. Well, one of. Then we went into nuclear chemistry, and we talked about the different types of radiation that come out of a nucleus: alpha particles, beta particles, and gamma rays. And we talked about two different types of decay processes: alpha decay and beta decay. In alpha decay, you lose an alpha particle, which means you lose a particle with 2 protons and 2 neutrons in it. In beta decay, when an atom undergoes beta decay, you lose an electron, which is also known as a beta particle. That's why they call it beta decay. And you lose that, though, from a neutron, turns the neutron into a proton and increases the atomic mass. The atomic number one on your isotope. Okay, so that's where we get transmutation. Transmutation is the changing of one element into another by either losing protons through a alpha decay, or gaining a proton through beta decay. There are other types of decay, but these are the ones that we're going to use to be representative. Okay, and then these things occur at a specific rate, and you can calculate them using what we call the half-life. The half-life is how long it takes for half of an isotope to decay or transmutate into another isotope. And based on that, you can figure out how long it's going to take to keep having how to keep dropping by half the amount that's left over. So we did some calculations using half-life, and with those calculations, we were um, able to calculate things like how old fossils and rocks were, because we knew the half-life of specific isotopes. If we can calculate how much of an isotope is left, we can figure out how many half-lives it's been around. And if we know the half-life, we can just go ahead and say, all right, well, the half-life of this isotope is 2 million years. In this fossil, it looks like um, a this fossil's been around for 4 half-lives of the um, of these isotopes life, and so 2 million years times 4 half-lives is 8 million years. Okay, so we did calculations with that. Okay, know how to do those. Once again, chapter 4 is going to be about 8 out of the 40 questions.